Well, we've been looking at surface integrals of real functions, scalar functions. Now we're going to look at surface integrals of vector fields. The flux of a vector field is the surface integral over S of f, the vector field, dot ds. Now that ds has a vector notation, it's got to because this is a dot product after all. They both have to be vectors, right? And it equals the surface integral over S of f dot n ds, where n is a unit normal vector to the surface S. Now we have to stop and talk about this unit normal vector. If our surface happens to be a function, then we can consider a unit normal vector that points up from the surface. But folks, as you know, there is another unit normal vector that points down from the surface. And that would be negative n. And so we actually have to know, should we be considering an upward orientation or a downward orientation? In the work that we're going to do, if we do have a surface that's a function, it'll be easy to see that our normal vector has an upward orientation because k will be positive, like the k component will be positive. But not all our surfaces are functions, and so we can say in general the unit normal vector n is given by the partial of r with respect to u cross the partial of r with respect to v divided by the magnitude of that cross product. So f dot ds, which is f dot n ds. Now this second ds is not a vector. We took care of the vector part by saying n, the unit normal vector, will equal f dot ru cross rv divided by its magnitude times the magnitude of ru cross rv dA, that last bit coming from the ds. And as you can see, the magnitudes divide out. This implies that the surface integral over S of f dot d vector S is equal to the double integral over d of f dot ru cross rv dA. Note, this is no longer a unit normal vector, it's just a normal vector where d is a projection onto a coordinate plane. We're going to note another similarity. Recall a line integral of a vector field is the line integral over c of f dot dr, that's vector r, is equal to the integral from a to b of f of r of t dot r prime of t dt. So once again, we have a dot product, we have a derivative. Here we have a dot product, we have a cross product of partial derivatives. This is kind of like a higher dimensional analog of what we had already seen in the past. Now, if we have that f is given by pi plus qj plus rk, and if z is equal to g of xy, so our surface is a function, then we have that the cross product of the partial of x, partial of r with respect to x cross the partial of r with respect to y is going to turn out to be negative partial of g with respect to xi minus partial of g with respect to yj plus k. And you can verify that by crossing the partial of g with respect to x 0, 1 with 0, the partial of g with respect to y 1. Now let me get rid of that. Then the surface integral over S of f dot ds is going to be equal to the double integral over d of the dot product of f and the cross product of r, x and ry. So negative p partial of g with respect to x minus q times the partial of g with respect to y plus r times dA. this cross product that we looked at, that I didn't do and said you could do, this partial with respect to x and the partial of r with respect to y, has as its k component a positive. With that positive there, we have that upward orientation. And I'm going to change the color of that. I made it red. I think I'd like it to be green. There. Because I'll use red to say if we had a positive in front of the partial of g with respect to x, a positive in front of the partial of g with respect to y, and a negative in front of the k, that is going to be associated with a downward direction, downward orientation. Now I need to point out that this positive or negative k only applies if our surface is a function. If it's not, then we're looking at RU cross RV. So we said that we were looking at flux, but what's the meaning of flux? So the surface integral over S of f dot ds, which is the flux, if f is equal to like rho times v, where rho is density of a fluid and v is a velocity field. That is to say, if v gives the velocity of a fluid that's passing through a surface S, and as I said, the fluid has density rho, then the flux is the rate of flow of the fluid through S. The meaning could also be electric flux through a surface or heat flow across a surface. Of course, that surface is given by S. So the meaning of flux is context dependent. It depends on what the vector field is. And this is more in the vein that this chapter was developed by physicists. Its applications are physical.